All right. Thank you very much. Good afternoon. My name is Evan Meade. I'm a rising junior at the University of Texas at Dallas studying physics and statistics. So this summer, I worked with Professor Matthew Penny here at LSU on simulating dithered microlensing astrometry for the Roman Space Telescope. Now, this was a really cool, interesting project because it deals with a classic sci-fi question, what are alien planets like? So in technical terms, we would refer to them as exoplanets. And in the movies, like Star Wars, there are these scenic vistas of far out places, but in reality, they're so far away and so dim that most of the time, they're just plots on our computer screen. There's something we have to infer their presence of based on other physical attributes. So why do we want to know about exoplanets? Well, knowing about what exoplanets are like in other systems can tell us a lot about planet formation even within our own solar system. And so NASA is creating an exoplanet census in 2 stages. The first stage was deployed with Kepler in 2009, and this looked at what are called hot exoplanets, which are those that are as close to the sun or closer than Earth. Whereas Roman, which is going to be launching around 2026, is going to use a technique called gravitational microlensing. And this will allow it to look at exoplanets that are farther than the Earth's orbit away from their host star. These are called cold exoplanets. So here you can see the phase space of different exoplanets and which mission is best designed to detect them. So you see that while Kepler captures a large number of great systems between 1 and 10 masses and about 1.1 semi-major axis, Roman, also known as W first until it was renamed, is going to open up a whole new part of the phase space, especially with more distant exoplanets. So what exactly is gravitational microlensing? Well, we know from relativity that massive objects distort space-time around them in a way that can bend the path of light. So if you have 2 stars passing in front of each other relative to an observer, then the one in front can act as a sort of lens which focuses the light of the star behind it. So as we can see in this figure here, this red star is acting like a lens for the yellow star. And so we get a corresponding peak in the brightness or flux over time. Now, if this red star also has a planet orbiting around it, then you'll see an additional secondary spike on the side here. And this is indicative of an exoplanet. And so this is great because it allows us to detect exoplanets that are in a very distant orbit or are very small. The downside is that in order to correctly mass them and not just have a mass ratio, we need to have stellar separation. So in the image, we need to be able to resolve the background star from the foreground star. So this is where Roman Space Telescope comes in. It's the next NASA flagship astrophysics mission, and it's expected to launch around 2026, featuring the Wide Field Instrument, which operates in the infrared band and has a similar resolution to Hubble, but covers a field about 100 times as large. So on the right here, you can see that 2 of these large yellow Roman fields cover the same area as over 400 Hubble fields. So because we are using about the same sensor, but over a much larger area, we run into something called undersampling, which is a technique that allows you to maximize your sampling area to theoretically increase your detection rates. The downside is that obviously you have fewer pixels on average per star. So it's affecting your resolution in a way that small pixel offsets, such as these 2 images here, are going to result in different appearances and thus different flux measurements, even if they're capturing the same star. So this is going to make resolution of stellar separation a lot harder and introduce some errors in our photometry. So now the question is essentially, how many exoplanets is Roman going to be able to detect? How effective is it going to be at capturing these microlensing events? And to answer this, in my project, I used the GOLS codebase, which was originally developed by my mentor a few years earlier to simulate time series microlensing data for Euclid and W first, which is the same mission as this. One of the key features of it is that it can precisely model point spread functions of the incoming light based on the physical attributes of the detector. So when a photon hits it, how do all the surrounding pixels read out that electrical value? I started off with some basic improvements, such as improving the statistical sampling of the star list that we use to generate these synthetic images. So if you'll look here, I've enhanced the view to reveal all the images, all the stars in the image, even the faint ones. And while these are real stars from real catalogs, the positions are totally synthetic. One of the main features that I added is dithering, which is the introduction of small translational or rotational offsets into a series of images. So in order to further maximize the detection rate, Roman is going to be pivoting from one field to another multiple times. And this means that when it returns back to a field it is previously sampled, it's never going to be able to return to exactly the same place. There's always going to be some sub or superpixel offset. And so this is reflected in dithering, where if you look, for instance, between the blue and red frames, we see that it's the same field, but captured over a translational offset. You can see for reference the same constellation highlighted in all 4 images. Additionally, we have a rotational offset between the blue and purple frames. Another factor that I added into the codebase was the introduction of proper motion. So as we know, the universe is not a steady state system. It changes and evolves with time, and one of those changes is the position of stars. So in this exaggerated simulation, we see the movement of stars played out over 300 years. Now, Roman's only going to be observing over the course of 5 years, but this is nonetheless a demonstration of the code's potential and features. So just to recap, my work allowed the user to specify 4 additional parameters when running simulations for each image captured. So you can specify a timestamp, 2 translation offsets, and 1 rotation offset. And this allows you to more realistically simulate the conditions of Roman imaging. Now, once you have this set of images, how do you actually use it and get something meaningful out of it? Well, one option is to try to do a linear combination of those images with something like drizzle. And this allows you to compile a set of images and align them and then stack them into a higher resolution picture. And while this introduces some noise correlation among adjacent pixels, especially in undersampled ones like this, it's still a robust state-of-the-art technique. The problem is that the state-of-the-art implementation is tailored almost exclusively for Hubble, so I was unable to get it to fully work with my goals images. That being said, this sample image on the left here, I created using Hubble data. So there is potential, but it requires more work. I had more success using subtraction imaging, where you take one reference image and then calculate a flux difference in all the other images. So this allows you to filter out constant stars and focus instead on ones that are brightening or dimming compared to the reference frame. So this will show essentially the peaks that we were looking at in the microlensing explanation, where a star will get slightly brighter or dimmer over time as another star passes in front of it. So here at the top, we see an example of difference imaging for ground-based data, and here we see it for my simulated data. And you can tell that it is a lot blurrier down here. So the pockets of white and black, which are brightening and dimming, are a lot noisier. And this is largely due to undersampling. So analyzing this, we can plot a measure of our uncertainty in the flux measurements against the magnitude of stars. And this is a naive implementation using a package called ISIS, which performs this image subtraction, and it is very flexible. So it was relatively easy to integrate it into the work. Now, the red line represents optimal performance, assuming no systematic error, and black represents actual performance. So any offsets are due to errors from undersampling and or physical design. Now, obviously, this has room for improvement. We can see 1 or 2 orders of magnitude difference among all these points relative to optimal. But even using just a simple method like a Gaussian convolution, which essentially just blurs out some of the errors in your input images, does an adequate job of correcting for some of this. So here we see that in the blue points, which especially towards the middle at around 18 mag, have a much lower error and are much closer to optimal than we see with a naive implementation. So this shows that there's room for expansion and growth in the methodology here, and that one day these may be part of the simulation and or actual pipeline for Roman data. So in conclusion, Roman is poised to play a very critical role in completing the NASA exoplanet census, and GOALS is an incredibly powerful tool which is going to help in the continued design and revision of the Roman mission. So in my project, I was able to implement a number of important features which allow goals to more accurately represent image capturing conditions of Rome in the microlensing survey. And I was also able to integrate it with different analytical packages. So with Drizzle, I was able to achieve a partial implementation and show that it's a promising technique in theory. And then with ISIS, I was able to get promising preliminary photometry and demonstrate that there is room for improvement with additional pre-processing of imaging. So in conclusion, special thanks to my mentor, Dr. Matthew Penny, the NSF for funding this, Dr. Hines and Dr. Jin, and all of my other associated people and institutions. So any questions?
I was curious with gravitational microlensing, this technique, how much information can you extract about the exoplanet? Like, can you extract information about its size or its distance from its host star?
Yeah, that's a great question. Yeah, so based on features that you observe in a microlensing event, it depends on what you capture. So in order to mask the star correctly, you have to be able to separate the main star from the background star. So in this case, you have to have an image that shows the yellow star being separate from the red star, and this allows you to compute a rough mass of the passing star, and then you use the mass ratio computed from the spike to mask the planet. And then as for distance, you can also compute that using the width of the spike, I believe. So in total, you should be able to plot any exoplanets you find on the same sort of phase space as the Kepler mission.
Just as a quick follow-up, does at least the spike that you had illustrated there, does the distance from the center of the main peak have anything to do with the distance of that exoplanet from the star? Does that give you some information?
That's a good question. So the distance of the secondary peak from the primary is just a result of when the planet passes in gravitational alignment with the lens acting as a star. Okay. So if it had been starting at a different point in its orbit, whenever the transit occurred, this spike would appear somewhere else. So the location of the secondary spike is basically random and just an effect of where the planet happens to be.
So it has to do with that three-body system and how it's all related to each other. Okay.
Exactly. Yeah.
Since you are in the slide, I was wondering, is this an experimental curve on the right-hand side?
No. So this is much too clean to be experimental. This is just a demonstration image created by NASA.
Okay.